The first problem, why aren't we getting a gain of -10 out of this circuit, is easily solved by noticing that R3 equals 1 ohm and is acting like a short on the input. Mathematically, this V minus would equal V source times 1 ohm in parallel with 10K divided by the 1 ohm series resistance plus 1 ohm in parallel with 10K, which would give about half the source voltage. The fix for this is to simply remove R3 because it's acting like a short. And this can just happen accidentally. This is circuit debugging. Adding a buffer works mathematically, but because it removes the RS, but R1 is still in parallel with R3, and so we're getting an RL of about 1 ohm. Load resistances on that buffer of 1 ohm won't work practically because the op-amp can only sink or source about 25 milliamps of current, and so you wouldn't really be able to maintain a full output voltage. Data sheets show that RL has to be greater than 2 kilo ohms in order for the op-amp to work. The next problem, we need to estimate how many parts would we need to implement these differential equations with op-amps. And there's two ways to do that. You could use this configuration for each variable where you have an inverting integrator and an inverting or non-inverting summer to bring in the initial conditions. Or you can use a switch to add the initial conditions, and then you can add negative or positive signals into this fully differentiated integrator. We'll do this method first. There are two variables, and there's two initial conditions, so that should be 2 variables times 2 op-amps per variable, 4 op-amps. I don't have to worry about plus or minus X or plus Y or minus Y because in this configuration I'm getting both variables. Given the signals, I need 5 resistances and 2 capacitors. In this method over here, I need only 2 op-amps, still 0 multipliers. The capacitors now jump to 4 because there's 2 of these per variable, and 3 resistances. These have to be well matched now because any variance between these 2 capacitors will put a common mode voltage on your circuit. I expected most people to follow this plan. In this problem, we were supposed to implement this equation into an op-amp based circuit. This gives us minus X. B is a function of time, and we just have to set this RC constant by setting C1 to 10, 1 over R5C1 equals 3, and now we can see both of these resistances should be 33K. Over on the summing side, because this is minus X, I want to keep minus X so that I can bring it in and integrate properly. So I use a non-inverting amplifier. By setting all these resistances equal to each other, let's say 10K, this just buffers these signals in a 1-to-1 relationship. This would be the equation that would be being solved, X equals XO, the initial condition, minus the integral. Here we needed to plot the transient response of this filter at 1K, 100K, and 900K. And we can calculate the gains of 10, 7.07, and 1, which then, if you multiply it by the input of 10 millivolts times a sine wave, you get 100 millivolts, 70.7 millivolts, and 10 millivolts. We can use this information to do the slew rate check, maximum slope, the amplitude of the output 2 pi frequency of the output times the max of a sine, which is 1. And we get these values over here. At 1K, 628 volts per second. At 100K, 44 kilovolts per second. And at 900 kilohertz, 57 kilovolts per second. None of these are slew rate limited. So that we can now just draw one period of the waveform at 1 over 1K is the first period, 1 over 100 hertz, 100 kilohertz is the other period, 1 over 900 kilohertz is the other period, and you can see the amplitude information matches. If I were to build a circuit to demonstrate the effect of V offset, I would just build a circuit that would measure it. One of the best circuits is this circuit mentioned in the homework solution. V out would equal 101 times whatever the VOS was. All I need is a DC voltmeter, power supplies, breadboard, and wires, and the resistance is shown, and this capacitor. I would measure these resistances with an ohm meter so that I could know exactly what that gain was. To extract ideality factor and saturation current from a diode, extract the slope and the intercept from the log linear relationship. M, these are the values I used, and I got about 40. And the ideality factor came up slightly less than 1, but that's due to reading the graph type of errors. This is what I got for B, and that's what I got for a current. Your values will change depending on how you extract it. Common problems are to extract here and here in the resistance areas, and sometimes to forget that that's millivolts. If you don't put in millivolts in your slope calculation or convert it to volts, you'll get a wildly different slope from that.